In this lesson, we will be focusing on dot products of vectors. So students will be able to calculate the dot product of two vectors. Students will be able to use the dot product to calculate the angle between two vectors and project one vector onto another. So there's quite a bit we're going to be doing with dot products. Our activator today, we looked at how to characterize a vector. We're given a vector. We talked about its magnitude and its direction. And in our instructional focus, we'll talk about, well, first off, what is this dot product? It's something you haven't heard about before. Finding a length, finding angles between vectors, and then something that we call vector projections. All right, so there's quite a few pieces that we're going to look at, and hopefully by the end of the lesson, they'll all tie together. Now, the concept of what is a dot product is one that's conceptually quite difficult. All right, so before we jump right into what a dot product is, or even what is it used for, we're going to talk about how we can calculate a dot product. All right, a dot product is simply taking the essentially the x value, the first part of a vector, multiplying them together, and adding that to the multiplication of the second part. So if I wanted to know what is u dot v, where u and v are both vectors, it would be u1 v1 plus u2 v2. This is just going to give us a number. All right, it's going to give us just possibly an integer value, but just a numerical value. All right, so a number by itself, it's kind of difficult to say, well, what does that number really represent? All right, but we'll get into that a little bit farther on. What I want to do first is make sure we're able to calculate the dot product. All right, there's some simple properties that are associated with the dot product. For example, u times v, or u dot v, is the same as v dot u. U dot u is just going to be the magnitude of u squared, which is pretty interesting. That's what that would get. 0 dot u gives you 0. U dot v plus w is u dot v plus u dot w. So notice that's just like saying, oh, we can use the distributive property, very similar in that regard. And with multiplication, some constant times u dot v is the same thing as saying u times that constant times v, or that constant times u dot v. So there's a lot of properties of the dot product that are very similar to the properties that you're already familiar with just straight multiplication. All right, and we're not multiplying these vectors. We're taking this thing called the dot product, and we use multiplication to do it. Remember, it's u1 times v1 plus u2 times v2. So if I wanted to go about finding a dot product, all right, I could go ahead and, for a here, for example, we have 3 comma 4 dot 5 comma 2. This would be 3 times 5 plus 4 times 2, which would give me 15 plus 8, which is 23. So essentially multiply the first two pieces together. Negative 4 plus negative 6 gives me negative 10. For the final one, we have 2 and 3, so 2 times 3 plus negative 1 times negative 5. 6 plus 5 should give me 11. When we take a look at the solutions, those are the same values that we got there. You might be wondering, what's with the I and the J? That's just another representation of vectors when we include that I or J when looking at a vector. Notice it's a slightly different form. We had either the vector notation with the bracket or a parentheses where we're including the I and a J. It's another way in which we can represent that vector. So now that we have an idea of how to calculate a dot product, let's calculate it for 3 different examples here. I've just drawn 3 different sets of vectors, and if we notice, in 2 of them, I've intentionally made them such that we have a right angle between them. All right, and I want to find the dot product in all 3 scenarios. So in the first one, we'd have 2 times 3, which gives me 6, plus 1 times negative 6 is negative 6, which would give me a dot product of 0. The second one, 5 times 6 is 30, plus 10 times negative 3 is negative 30, gives me, once again, 0. The third one, 2 times 4 is 8, plus 4 times 1 is 4, gives me a value of 12. Interestingly enough, all right, anytime two vectors are perpendicular to one another, their dot product will equal 0. The dot product, so going back to that question of what is a dot product, the dot product helps us to determine the angle between two vectors. In every time we have perpendicular vectors where they form a 90-degree angle, their dot product will always equal 0. All right. So that's just something to know. All right. If we know that's a way to determine if vectors are perpendicular. It's just one way to do it. But it also helps us to understand something about the dot product, that it helps us to understand the angle between two vectors. A second thing we can do with the dot product is we can determine the length of a vector. So if I wanted to find the length of vector u, if it's 4, -3, I could just do u dot u. So I would do 4 times 4 plus -3 times 3. Gives me 16 plus 9 is 25. And that's going to be the magnitude of u squared. So if I just want the magnitude or the length, I would take the square root and I would get 5 as the magnitude of u. Now, once again, I mean, this is essentially what we would be doing if we just found a triangle that said a squared plus b squared equals c squared. But it's interesting to know that if you take the dot product of a vector with itself and then take its square root, it will give us the length of that particular vector. And we can see that here, that the magnitude of that vector is just going to be the square root of the dot product between them, which works out just as we showed in our example. One other thing we can do, and once again, we talked about how the dot product can be used to find that angle between vectors. We only talked about 90 degrees if the dot product was 0. But there's something else we can do, all right? What's super interesting is if we do u dot v divided by the magnitude of u times the magnitude of v, that will give us the cosine of the angle between them. All right, and one way to think about this is, u divided by magnitude of u, this is just the unit vector, right? Unit vector in the direction of u. V over magnitude of v is the unit vector in the direction of v. So the dot product of the unit vectors will provide us with the cosine of the angle between them. So we could just take the inverse cosine of that dot product and it will tell us the angle. So now if the dot product is 0, well, the inverse cosine of 0, guess what that is? Inverse cosine of 0 is 90 degrees or pi over 2. That's how we knew that two vectors are perpendicular if their dot product is 0. But if their dot product is not 0, we can still use it. We divide it by the product of the magnitude of the original vectors and then take the inverse cosine, and we can know exactly what that angle is between the vectors. So here's an example of this. We could use an algebraic method to find the angle between them. All right, and we can use a calculator to approximate. So if I wanted to find the angle between these vectors, right, we would need to find their magnitudes, take the dot product, divide by the product of the magnitudes, and then do an inverse cosine. So let's take a look at the solution from the book. All right, they set it up. It's just going to be the cosine of theta is u dot v, which they find on top, divided by the magnitudes times each other. So they do the magnitude of each vector, which they calculate by either doing a squared plus b squared is c squared, or the square root of the dot product of itself. And they get this value 11 over radical 13 times radical 29. And then they take the inverse cosine to get 55.5. So we learned that the angle between those two vectors is 55.5. Now we can do the same thing on the second one, and you would find that the angle is 135 degrees. All right, so we can go through this process where we take and find the dot product of the vectors divided by the product of their magnitudes, and then take the inverse cosine. And that tells us that angle between them. That's why the product or the dot product of two perpendicular vectors will always be 0, because the cosine of 0 is 90 degrees. So there's a name for it when two vectors are perpendicular, when that angle between them is 90 degrees, and we call them orthogonal vectors. So vectors u and v are what we call orthogonal if and only if u dot v equals 0. All right, so if we wanted to prove that two vectors were orthogonal, all we would need to do is take their dot product. We could do 2 times negative 6 plus 3 times 4. We find negative 12 plus 12 equals 0. The dot product equals 0. Therefore, they are orthogonal. Solution of the book, that's all they do. They take the dot product. The dot product gave them 0. The end. That's it. So if we say, hey, can you prove that these two vectors are orthogonal? Take the dot product. Is it 0? Then they are. If it's not 0, then they're not. So all of this leads us to this next concept, which is what we call a projection of a vector. So if I have two vectors, I have u and I have v. All right, and I want to know, well, what is the projection? All right, what is the projection of u onto v? I want to know, for example, what portion of u is exactly on v, all right? And that kind of sounds like, what is he even talking about? So let's take a look at this diagram right here. I have my original vector u, all right? And I have a second vector v, which is pointed down in the other direction. I'm going to keep these colors separate just so we can really differentiate between what I'm talking about. So let's go with one of them is going to be this bright green that's going to come down here. So here's u, here's v. All right, so u is in blue, v is this orange. Now, I could break up u into two component vectors. All right, and I want these components, one of them, the components, to be exactly on v, meaning it's just part of vector v. All right, and that's what this red vector is right here, this u1. I can say u is composed of u1 plus another piece, u2, which I'm going to make just like an orange. All right, this u2 that comes up here, and they form a 90-degree angle. So I could say u really is made up of two different vectors that are added together, right? We've learned that we could add two vectors together, and the resulting vector is just where the final vector ends up. So u could be made up of this u1 and u2, where u1 is the portion of u that is right on top of vector v. And that's what I'm looking for when I say, what is the projection of u onto v? It's really kind of how much of u is made up of vector v. So what part of u would be like right on top of vector v if I had to break u into two different pieces? And the way in which we do that is we follow this formula right here. This projection of u onto v is just u dot v divided by the magnitude of v squared times v. And you might be like, whoa, that's a lot going on there. All right, and what we're really trying to do is we're trying to break vector u down into two pieces. All right, where one of those two pieces is that projection of u onto v. So if we go through and break down that formula, we can rewrite u as u1 plus u2, where u1 is the projection of u onto v, and u2 is just u minus u1. All right, because we know that if the two add up to get u, then if we subtract the piece away, then we can find what that other piece would be. So I know u2 very easily is just u minus u1, right, which gives me this 4, 4. I know that this piece right here, this u2 piece, right, that's the vector 4, 4. Well, u1 is the projection of u onto v, which is just that u dot v, right? 6 times 5 is 30, plus 2 times 5 is negative 10, so 30 minus 10, that's where the 20 comes from. The magnitude of v is just 5 squared plus negative 5 squared. Take the square root, gives you the square root of 25, or sorry, the square root of 50, because 25 plus 25, right? So I'll do that here. It's just 5 squared plus negative 5 squared square root. That gives me the square root of 50, but I'm going to square it because I need the magnitude squared. So that's where the 50 comes from, times the original vector, 5, 5. So it's 20 50ths, or 0.4, 4/10, or 1 2/5 of 5, 5, which when we multiply that out, 20 over 50, or 2/5 times 5 gives me 2. 2/5 times negative 5 gives me negative 2. So my projection of u onto v is 2, negative 2. And I can find that if I add those vectors together, did I get the original? I did. So that's a way in which we can know, yep, it worked out. We were able to determine the two different components. But the big piece is getting this projection. How do we get the projection? We just follow that formula. We find u dot v divided by the magnitude of v squared, and we multiply that times vector v. And it tells us what portion of u lays right on top of vector v, and that is what we call a projection. That's the projection of u onto v. All right, so how might we apply that formula, that one that we just used, where we said, if I want to know the projection of u onto v, right? This formula from a couple slides ago, the projection of u onto v. Projection of u onto v is going to equal, remember, it's u dot v divided by the magnitude of v squared times v. All right, so this is what we're going to try to do. We're actually trying to, in this scenario, we have Juan sitting on a sled of a hill that has a 45-degree incline. The weight of Juan plus the sled is 140 pounds, and that's being pulled straight down. So there's like a vector with the magnitude of, say, 140 going downward, right? And I want to know, how hard does Rafaela need to pull in this direction up the hill to prevent the sled from going down? Well, in order to do this, I need to find what is the projection of that force F onto the hill. All right, I don't necessarily know, what that magnitude would be or how far that would be, but I need to essentially project that 140-degree straight down vector onto the hill. So the way in which we go about doing this, all right, is we need to first start out by how can we represent the original vector. We represent that vector, we'll call it that force F, all right, is negative 140j, because j represents that vertical up and down. And it's negative because it's downward, it's straight down. Now we also want to have a vector that we want to project it onto. The vector we want to project it onto is this vector right here, the one that represents the side of the hill. Now, the magnitude of this vector does not matter, all right, because we're going to take care of that when we do that division by the magnitude of v. We just need a vector in that direction. So we're just going to look at the unit vector, all right, in that direction. Because this is a 45, 45, 90 triangle, I know that the side for the x value is just represented by cosine 45 times whatever I is, and the y value is sine 45i, right? Well, and I know sine 45 and cosine of 45 are both square root of 2 over 2, so I know that that vector can be just represented by this, which is going to be my unit vector, right? This is just straight from our unit circle, right? We know that the radius in this case would be 1, all right? And because that radius would be 1, that would be that magnitude of that vector. So this is the unit vector, which is really nice, because then when I do my projection, I just have this magnitude of v squared. Well, that's just 1 squared, so I can just get rid of it. So the projection is just going to be f dot v times v. Well, f, all right, is 0i negative 140j, right? Because of that first one being 0, when I multiply 0 times radical 2 over 2, that just cancels out, and I'm only left with the negative 140 times radical 2 over 2v. So at this point, if I wanted to get the final vector f1, I would go ahead and multiply by vector v, which was the radical 2 over 2i plus radical 2 over 2v, which would give me negative 70 I plus j. But we didn't want that final vector. We actually just wanted the force that needed to be pulled, which was the part that we found first. So it's this negative 140 radical 2 over 2, which is the same thing as negative 70 radical 2. So that's the force down the hill. So in order to keep the sled from sliding down, I need the opposite of that, which means I change the sign to positive 70 radical 2, which tells me the pounds of force needed to be pulled in the opposite direction. So another application of vectors is in calculating something called work. All right, in science, we can calculate work by taking a look at a couple things. So starting out, if F is a constant force whose direction is the same as the direction of AB, the vector AB, then the work done W by F in moving an object from A to B is just calculated as the magnitude of F times the magnitude of the vector. But if F is a constant force in any direction, then the work done by W by F onto moving an object from A to B. So for example, if I had something like this where I have A here, B here, right? And some object is going to move. So say I had a box and it moves from A to B, right? But the force was being pulled in this direction and over, it's able to move from A to B. I want to know what work was done. We would actually do the magnitude of F. So F, this is F. It would be the magnitude of F times the magnitude of AB times the cosine of the angle between them. All right? And that might sound a little bit confusing. So let's take a look at an actual example. So if I want to find the work done by a 10-pound force acting in the direction 1, 2, and I'm actually going to draw a little graph of this, of what this would look like. So I have 1, 2. So I actually have a force in this direction. All right? And it pulls something from the origin all the way out to 3, 0. So it's very similar to that original scenario. So it pulls a box to the right. And I want to know, well, what was the work done by that force in moving that object 3 feet from 0, 0 to 3, 0? We're going to start out by determining the vector, all right, for F. Now it's a 10-pound force, and it acts in the direction of 1, 2, but it's not the vector 1, 2. So in order to actually figure out what vector would be represented by this, we actually need to take that 10 and multiply it by the unit vector in the direction 1, 2, which is just vector 1, 2 divided by the magnitude of 1, 2. That would give us that unit vector. And so the magnitude of 1, 2 is just the square root of 1 squared plus 2 squared, or the square root of 5. So when I actually multiply that out, my vector F, right? So this is different than the force F. It's the vector F is going to be that force 10 times the unit vector in the direction 1, 2, which gives me the resultant vector of 10 over radical 5 times the vector 1, 2. All right, so that gives me the actual vector represented by F. Now that I have that vector represented by F, I can go ahead and determine the work done by taking that vector and not multiplying, but taking the dot product of that vector and the and vector AB. So it's going to be 10 divided by radical 5 times the vector 1, 2 dot the vector 3, 0. So 1 times 3 is 3, 2 times 0 is 0. So that's just going to be 3. 10 times 3 gives me 30, and it's 30 divided by radical 5, which gives us 13.42 foot-pounds, where foot-pounds is the unit that we use in this particular problem. So in this lesson, we learned a lot about vectors, and specifically the dot product of vectors. We learned how it can be used to analyze the angle between two vectors and to project one vector onto another, which is a massive concept, and I know in a single lesson it's a lot to take in. We talked about this idea of vector projections, and it allowed us to solve real-world problems around us. So you should be able to determine a dot product. You should be able to use a dot product to find the length of a vector. You should be able to use the dot product to determine the angle between vectors, to project a vector onto another, and then you should be able to solve problems that are related to physics using a dot product.